So now you have obtained the coefficients or the a values which characterize the displacement functions in the x and y directions. Yeah. So we already so we know that alpha, beta, and gamma we know because we already know the nodal coordinates, and the unknown displacements are of interest, which is ui, uj, and um. Of course, vi, vj, and vm are important now. And how can we find them? Since we can really find them now because we already found a values. Yeah. So if we write down in general, what we are interested is in obtaining the displacement function in u in x direction as well as y direction. It is nothing but this equation which we derived when we use this equation when we define the displacement functions. So since we already found out a1, a2, and a3 using equation 5.2.1 here, we can simply substitute this value and obtain a generalized displacement function for u. Yeah, so u is nothing but so a1, a2, a3 contains 1 over 2a. We take it out, and of course 1x and y, this matrix will be the same here, and it has to be multiplied by the alpha, beta, gamma matrix and the corresponding displacements. When we simply work out this matrix or try to solve this matrix, you would end up, if you multiply the alpha terms, do the matrix multiplication, you would end up in getting equation 5.2.5. I mean, these are really straightforward. I need not write step by step in order to save time. I have just given the answers directly to you all, so you can leisurely check these derivations step by step and get familiarized. So up to now, there's nothing new. Okay, this is simply matrix manipulation, simple linear algebra, nothing new. So by let's say we have obtained now two matrices by multiplication, by considering the multiplication between the alpha, beta, gamma matrix and the displacement matrix, ud matrix. We have obtained one single bulk matrix, and the next step we try to multiply these two matrices, and what you would end up is getting an equation as a function of x and y for the displacement in the x direction. Yeah, so likewise you could follow the same procedure and obtain or you can simply replace ui, uj, and um by vi, vj, and vm and obtain a displacement function in the y direction, which is given by vy. Yeah, so now we have the two displacement functions using the of course in the x and y direction using the nodal coordinates, yeah, for describing the behavior of the elements. Now, as we already know in the previous case also, this is again a simple definition, nothing new. You can use this since you have obtained, let's say, okay, let me be clear. Now you obtain two displacement function in u, x, and y direction, which is given by u and v, and you have obtained it using displacements in the x direction for the three nodes. And you see here the let me check. Sorry, these have been multiplied by certain let's say constant values, of course constant as well as a function of x and y. You can see these functions let's call this as interpolation functions, so shape functions, just like we did in the previous case. So simply we call them, let's call them ni, nj, and nm. Okay, so nothing new here, just simply you have made a definition, or may have you have come up with a definition saying that ni, nj, and nm are expressed in terms of the alpha, beta, and gamma values, and in terms of coordinates x and y. Okay, right. Where are we now at? Now, I think you get the whole intention. Now we are trying to, since the expressions are getting longer and longer, we try to use simple forms and we try to introduce shape functions. You know, when we define interpolation or shape functions, they had certain properties. We already discussed it in the previous sessions. So we define this the displacement in form of the shape functions and write the matrix, the displacement matrix, the general displacement matrix in a more, so to say, in a more elegant way using the shape functions here. It's nothing new. Matrix, coming up with definitions and matrix rearrangement. Okay, now we have already come up with a generalized displacement function, which is nothing but given using the shape functions or interpolation functions multiplied by the displacement functions, which are expressed, these are already expressed now in terms of the nodal displacements or nodal degrees of freedoms. So now we have almost come up to a let's say come up to a, let's say we have significantly progressed when in the derivation of this constant stiffness matrix for this concentrated triangular element matrix. So movements, or let's say, if we, since we considered a small element like this, these elements are subjected to different modes of displacements. It can be this, or they can be subjected to different motions of rigid body motions. They can be, they can translate, or also they can rotate. Translate in x direction and y direction, as also rotate in the xy directions. Yeah. So if we, for example, if we now consider, let's say, a simple, let's say, cantilever beam, which is subjected to a certain load, you know, this total beam now can be this total plane stress problem can be characterized or can be captured using plane stress, or we call it concentrated triangular elements. Yeah. So what we do is, now you can see how this problem has been segmented into concentrated triangular elements. You would see that in this cantilever beam, some portions of this cantilever beam, they undergo a rigid body motion, because this the load applied in the middle is really kind of like the nodes, or the, let's say, elements which are situated at the very end of the beam are less subjected to this load. So most likely these elements will undergo a rigid body motion. Either it will undergo translation as well as a rotation. Yeah. So we have to take such things also into account when we are defining the matrix. So just a note on that, just a side note. In order to illustrate the modes of, let's say, for the plane strains condition, to satisfy the plane strain condition, the rotation, okay, the straining due to the rotation, as well as, of course, the transformation translation has to be taken into account. So the idea is just to show you how this cantilever beam has been modeled with the plane stress elements by considering rotation and stretching, as well as changing of the shape by taking in such things into account, which we have already considered when we are deriving this element stiffness matrix. Okay, and in the next step now, as we did in previous cases, what we have to do is we have to define the stress strain relationships, and of course the strain displacement relationships. Yeah, and since we already know that these elements are subjected to rotation and translation, we already defined how the rotations, or quantified the rotations and the translations in the previous figure. So if you can recollect, we'll just yeah, this figure, if you can remember, when we consider this finite element component, we considered this infinitesimal element, and we considered how it has been subjected to translation as well as rotation. Yeah, and by coming up with certain definitions for the strains and the stresses, as well as shear strains, we wrote down some definitions. We will be using now these definitions in order to now relate the stress strain relationships, or the stress strain displacement relationships. So I know this derivation is quite lengthy, you have to bear with me, and I know this is up to now, this is nothing new. You just have to know how this is derived. I cannot just show you the results as that this has been fallen from the sky, but I try to show the derivation and try to motivate you so that you will try to devote your time on your own and try to get familiarized with these derivations. Okay, right. Let's now define the stress displacement and the stress strain relationships. So when we talk about the stresses or strain matrix, we have three strain relationships. We have the strain in x direction, strain in y direction, and of course the shear strain, which we can characterize using the displacement functions, and by taking the partial derivatives of the displacement function. Yeah. So from here onwards, there are additional details coming into play. I mean, it's not additional details. I will just only highlight what we have done, and this is somewhat the important points maybe which you can keep in your mind, and after the lectures you can just go through the lecture notes, browse reference material, and try to get familiarized with the derivations. But for solving the problems and tackling the problems, this is not really required, so I will only highlight what is really important for you to understand and to tackle the problems that we will be solving within this FEM course, because and leave the derivation, how to go through the derivations, up to you, because I've already, okay, you just have to go through these lecture notes, it's all there, and if you have any concerns you can ask me, but I will try to highlight only the, let's say from this point onwards, I will try to highlight only the, let's say, most significant or important points you need to keep in your mind. So why are we doing this now? We already came up with we already selected an element. We came up with displacement functions, which can be described using the nodal degrees of freedom. Now we would like to relate these displacement functions to the stresses via stress strain relationships. For that, we have defined the strains, and now we are explaining, or we are using the strains. Yeah, we are using these strain values and expressing them in terms of the shape function. So the internal, let's call it them, the internal, we use this strain and explain them using nodal degrees of freedom and together with the shape functions. This is the thing that we have already done. So we have yeah, so this is the only thing that we have done here by so we have used a certain terminology. You can go through these sections on your own. I will just highlight what is important. You can see here nothing but you have explained the strains, the axial strains, the strains in the x direction, y direction, as well as the rotations using the displacement functions here. This is nothing new, just as well as the area of the triangular element. So by simple substitutions, you would end up in getting the strain matrix, yeah, with the help of alpha, beta, and gamma. Of course, in this case, beta and gamma values can be used. It's multiplied with the displacement functions to express the strain matrix. And what is important to remember is that this strain matrix has can be expressed in terms of a so-called B matrix. This is important. Yeah, when you're solving these problems, you will be given these matrices wherever is necessary. You don't have to memorize this. So B matrix is nothing but let's say a matrix which includes information based on the nodal coordinates. Yeah, because beta and gamma, these are already constants which include which are functions of the nodal coordinate systems. So the strain matrix can be defined using three components based on the patterns you can see. Okay, let me just for you to, these correspond to I node, these sections correspond to jth node, and this in the matrix this corresponds to mth node. So keeping that in mind, or by following this let's say pattern, we have already come up with three matrices. Yeah, three matrices like this, which segments the ith component, or corresponding to ith node, jth node, and mth node. Yeah, and you have only simply written down the displacement matrix on the right hand side here. So the corresponding components, of course, for BI, BJ, and BM can be written. And just a note on the B matrix. So this is, you may have realized now, this is nothing new. Yeah, I have used just a certain set of terms in order to define another set of terms. So I have used now a so-called B matrix. This is the simple, in simple terms, what I have done is I use an additional another matrix called a B matrix in order to relate the strain matrix to the displacement matrix. And what is this B matrix? It is nothing but a matrix which contains information based on the nodal coordinate systems, based on the nodal coordinate systems corresponding to the ith node, jth node, and mth node. Simple. So what is important for you to remember is B matrix is kind of independent of these xy coordinates. Yeah, so they are kind of constants. They are only dependent on the elemental coordinates, because you will see that these components are Bi, Bj, and Bj are constants, which are just values which you would get by substituting the nodal coordinates. So these are depend only on the nodal coordinates. And of course, you see in the strain which we have described using this equation 5.2.33, since this is constant, of course, the strains which we defined would be constant, which is given by equation this 33. And this is the reason why we call this to be a constant strain triangular element, because the strains, the resulting strains will be constants. Yeah, so this is why we have defined it to be a constant strain triangular element matrix. So simply then the next step is, since you already know the strains, you can relate the strains to the stresses. Simple, the next logical step. We know the three strains now, we know the strain matrix, and we can relate it to the stresses. How do we relate it? We know the constitutive matrix we already learned about for plane strain and plane stress problems. If it is a plane strain problem, with the help of Young's modulus and Poisson's ratio, we can define as the matrix, the constitutive matrix or the stress strain matrix is given for a plane stress case, and a slightly differing matrix form of a matrix is given for a plane strain case, again using the material properties such as the modulus of elasticity as well as Poisson's ratio. Yeah, so then you have already applied, obtained the stress strain relationships. Now it is simply, if you substitute the values which you have got, of course, sigma, the matrix sigma is equal to the D matrix times the epsilon matrix, since the epsilon matrix can be explained using, or can be derived or can be written using the B matrix, and the displacement matrix, we can write the stiffness matrix to be equal to D matrix times the B matrix, the constitutive matrix, the B matrix, which is nothing but the function of, or let's say nothing but a set of constants which equal nodal coordinates based on nodal coordinates, and of course the D matrix, which is the displacement, the function within the element.